My name is Tyler, and this is my final project for Calculus 2 at UIS. Today I'm going to be talking to you about quaternions, their history, examples of calculations, and some of their applications. So you may be wondering what was that video with the paper airplane about, and that will get explained here shortly. As you can see, the plane was rotating from its initial position. There's a way to mathematically describe this rotation as you saw it, but this requires what's happening now, a quaternion. Now you ask, what is a quaternion? Well, a quaternion is a higher-order complex number that builds off of the complex or imaginary number system. And for the purposes of this video, quaternions will be written as capital Q are equal to A plus BI plus CJ plus DK. And you'll learn more about this notation later, and I'll explain what these mean. Before one can dive into the world of quaternions, the topics of imaginary numbers, complex numbers, and the complex plane must be addressed. The imaginary number, I, is called the imaginary number because it's just that, imaginary. I is equal to the square root of -1. It's impossible to have the square root of a negative number because two of the same number with the same sign when multiplied together will always be positive. For example, 2 times 2 is equal to 4, -1 times -1 is equal to +1, and so on. Complex numbers consist of a real part and an imaginary part. The real part is a real number, and the imaginary part is a number with I attached to it. Now to go over the idea of the complex plane. This is a way of showing the real and complex numbers together in 2 dimensions. If you draw 2 axes perpendicular to each other and label the x-axis as the real numbers and the y-axis as the imaginary numbers, then by writing a basic complex number such as 2 plus 2i, with 2 as the real part and 2i as the imaginary part, and which also means to go over 2 units in the x direction and up 2 units in the y direction, you now have a coordinate on the plane. A similar way to how the regular coordinate plane relates an x and a y, the complex plane relates real numbers and imaginary numbers into a coordinate. Now, the complex plane is a good way of representing the locations of things in 2 dimensions, such as on maps and describing their coordinates. But what happens when there's multiple coordinates and we need to describe an angle between them, or we need to rotate in the plane between coordinates? As we saw earlier in the semester of Calc 2, Euler's formula has a similar look as the complex number. Thanks to Leonhard Euler, who proved that e to the I theta is equal to cosine theta plus I sine of theta, the polar coordinate with the theta and the Cartesian coordinate, or the x and y, can be related. Introducing an angle, theta, allows for rotations and finding angles between the coordinates on the plane. With that out of the way, we can move forward into actual quaternions now. So we fast forward to a beautiful day in 1843 as William Rowan Hamilton is walking to a meeting of the Irish Academy, intrigued by the utility of using Euler's formula within 2 dimensions and the capability of using it in 3 dimensions. Hamilton wanted to find a way to represent rotations in 3 dimensions, similar to a way that Euler's formula makes it possible in 2. Hamilton, with a quick, ingenious thought, created 2 more complex numbers, j and k, to create the concept of quaternions, and he wrote all this into the stones of a bridge on the Royal Canal. While the original writing that Hamilton put on the bridge isn't there anymore, you can still see today the plaque that they put up where Hamilton had this thought, and on it you can see that j and k, the other 2 complex numbers he created, are written with I. And the formula I squared is equal to j squared is equal to k squared, which is equal to ijk, which is equal to -1. And this gives the formula for a quaternion and sets up some of the rules that I'll talk about later. A full quaternion, making use of these extra complex numbers, is written as q is equal to a plus bi plus cj plus dk. I, j, and k represent the imaginary number I and Hamilton's extra imaginary numbers j and k, and a, b, c, and d represent real numbers, just as a and b do in the notation a plus bi, or 2 plus 2i as I showed earlier. In order to extend the system of complex numbers already in place by creating j and k, Hamilton also had to create a set of rules which govern these complex numbers, and they are shown here. One important quality to keep in mind is that the quaternions are not commutative, so the order in which they are multiplied is important and has to be kept track of. The rules are ij is equal to k, j times i is equal to -k, j times k is equal to I, and k times j is equal to -I. K times a is equal to j, and I times k is equal to -j. You can see that as the order is flipped, the sign also flips for the product. The rules can be arranged into this multiplication table, which explains how they relate. The rules I just mentioned, in addition to those Hamilton wrote on the bridge, are all combined into this table, and you can see it here. Furthermore, the j and k imaginary numbers can be included into a plane as well. The regular 3-dimensional plane includes a z-value in order to give the plane 3 dimensions. I, j, and k serve this purpose for the complex 3-dimensional plane, just as the real numbers and I do in the normal 2-dimensional complex plane. As you can see here, x, y, and z match up with I, j, and k. A is the value for the size of the quaternion, or essentially how long it is, and it's not shown here. But this graph essentially shows the three-dimensional plane in which we can do rotations with quaternions. Now to move on into some actual calculations. Quaternions can be added just like regular complex numbers can, and they follow the same rules. For example, in the addition of the quaternions 4 plus 6i plus 8j plus 22k and 8 plus 97i plus 42j plus 8k, as you see here, the like parts can be combined, and this results in the addition quaternion of 12 plus 103i plus 50j plus 30k for this example. In taking these same two previously mentioned quaternions, we can also multiply them together in the same way that regular complex numbers can be multiplied. And using the same two, written at the top of the paper here, distributing and multiplying through results in a mess of numbers, signs, and letters. It is important to follow the rules here, as you can see. The terms with two imaginary numbers, such as j and I, j and j, j and k, or k and I, result in different imaginary numbers or a different sign, or anything can change in the term. So it's important to keep track of all the previously mentioned rules and to follow through with the multiplication table. The mess of numbers previously shown can be cleaned up very easily with following the rules shown on the left here. The notation A1 means the A value for the quaternion written as Q1, B is for the B value of Q1, and so forth. When multiplying through the quaternion, this results in the same answer in a much neater way, and this leads up to the idea of rotation matrices. By organizing the multiplication into such a way, this leads into the idea of what are called rotation matrices. These matrices here are those that can be used to find the rotation of an angle, theta, around the x, y, and z axes respectively. By multiplying the matrices by a point with three parts, then you can calculate the new x, y, and z, or I, j, and k values for the point after your rotation. For example, to rotate the point with the coordinates 1, 2, 3 around the x-axis, you would multiply that point, 1, 2, 3, and its coordinates by the rotation matrix denoted by r sub x up at the top. So as I said earlier, if we define a quaternion as q is equal to a plus bi plus cj plus dk, with a as the size and b, c, and d representing the location and the various parts of the 3D coordinate plane, as you can see on this graphic, this is similar to the way that a plus bi shows a location on a 2D area. I'm going to throw more notations at you, but these are necessary for describing a rotation. If we have an angle which we want to rotate by, theta, let's say, then we can incorporate that angle into the quaternion. But first, we have to represent the axis of rotation, or the axis around which the rotation we want to make, which is also sort of a point that can be represented with three coordinates, an x, y, and z. And keep in mind that these equate to I, j, and k in the complex coordinate plane that I previously described. For this notation, we can relate the a, b, c, and d values to theta with the notation shown on the screen. These are a is equal to cosine of theta over 2, b is equal to x, or the first part of the coordinate, times sine of theta over 2, c is equal to y, or the second part of the coordinate, by sine of theta over 2, and then d is equal to z, or the third part of the coordinate, times sine of theta over 2. So we just need one more part in order to do the rotation calculation, and then I promise I'm done introducing all the different notations needed. The last part needed is the conjugate of the quaternion, and that is simply q to the q star is equal to a minus bi minus cj minus dk. To tie all this together, we can perform the rotation by multiplying the quaternion, its conjugate, and the point of axis of rotation with the three coordinate parts, and this product of the multiplication describes the location after the rotation has been performed. And I know it's kind of confusing, but this results in a new quaternion in the 3D space. For this video, I'll write that product as x, and you can see that it's the product of q times p times q star. I know you're probably confused, and you might be wondering how all this information and crazy calculation can be used in the real world, and they are particularly useful in two settings. These are describing the ways in which planes and other aircraft, such as the space shuttle, can rotate in the sky, and describing the orientation of an image in computer graphics within programs and video games. For planes, the chart shown here describes the ways to rotate, or ways the plane might be desired to rotate, but it is given different terms. Instead of having an x, y, z, or an I, j, k coordinate type configuration, the terms pitch, roll, and yaw can be used. Yaw describes the rotation around the vertical axis, which is usually the y-axis, while roll and pitch describe the z and x axes respectively. Describing these orientations mathematically with quaternions is important in orientation and navigation of the plane. Within computer graphics, quaternions are used to rotate the frames for an image so that the camera can appear to follow a character and rotate as needed for the game to run as desired. A good example of this is the first Tomb Raider game, where quaternion calculations are needed for the camera angle as the camera follows the player through the winding areas of a tunnel. That's all for this video, but I hope this has been very informative to you about the topic of quaternions. Thanks for watching.